Okay, let's do the classic problem once we know that the electric field inside a conductor is zero. Imagine, if you will, that I have two conductors that are right next to one another. They're two parallel plates. They're separated by a distance L. Right? And there's some area A. The question is what is the capacitance between those two plates? And for capacitance, we're going to need Q over V, right? Q over the voltage, because that's how capacitance is defined. So, well, since these are both conductors, well, I can start to think about the problem by using Gauss's law. I imagine I have some positive charges here, right? I can draw a Gaussian surface. Now, there are going to be three things on this surface. There's going to be down in here in the gap. This is in the gap where there's nothing, this part here. The electric field is going to point away from the positive charges, and the area is going to point away from the Gaussian cylinder. So for that surface, it's going to be EA. Well, we know that the electric field is pointing away from the positive charges, and from the side of the Gaussian cylinder, that's going to be, the area is going to point perpendicular to the field lines. So when I do E dot dA, EA cosine theta, I'm going to have them be perpendicular, so that dot product is going to give me 0. And now you might say, well, what about the top part here? But that side is inside the conductor, right? And we know that the electric field inside the conductor is 0. So we get 0 here. And of course, Gauss's law is equal to the charged enclosed over epsilon naught. So we'll just write Q for the time being. And so I get that E is equal to Q over the area epsilon naught. Okay, where do we go from there? Well, we know that the electric field now is going to be constant, right? It's going to be a constant value going from the top down, at least as an approximation. Right at the ends it won't be, but in the core of the capacitor, it's basically going to look like that. So now, if I know that my electric field is equal to Q over area epsilon naught, now I can do my integral to find the potential. I know that the potential is equal to E dot dl, right? Of course, going in the direction, I've just dropped the negative sign because it doesn't matter here. So I get V is equal to QL over area epsilon naught. And now I want to rearrange this equation to get Q over V, because that's going to tell me my capacitance. So I can get that by dividing through to get Q over V, right? And that is going to give me area epsilon naught over the length. Now, what's important about the capacitance? Well, the great thing about the capacitance is it only depends on epsilon naught and the geometry, the area of the capacitor, and L, the distance between the two plates. And so the capacitance doesn't depend on the charge, it doesn't depend on the voltage. It's independent. It only depends on the material and the size of the object. This is important because later on you'll find that it also depends on the material, or this epsilon or epsilon naught. So there's going to be some dependence on the type of material that's inside. So if you just have air or vacuum like we do here, it's just epsilon naught. That's the classic capacitor problem.